This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. So in the last lecture I stopped with virtual short, and then we also discussed how to explain the amplification of operation amplifier without using any equations. Using the concept of virtual short, we discussed the amplification using the operation amplifier. So today again we are starting, because this is an important concept. So when you have operation amplifier, what you are getting is the open loop mode. Means this operation amplifier, it won't got a gain. So that gain is the internal gain of the operation amplifier that you are getting because of all the transistors inside and the load resistors they already decided. So then this, when you have this operation amplifier, you can operate in two modes. So one is open loop, and then another one is closed loop. So we already discussed the open loop example, that's a comparator. So comparator is an example for operating in open loop. Then closed loop, so amplifier, filter, oscillators, etc. So you find many applications in the closed loop, but you will find only a few applications in the open loop. For example, comparator. When you are using the open loop, then what you are using is you don't have no control over gain. Means you are using the open loop gain, the very large gain. Then again, no control over free bandwidth. So then you will be using the available bandwidth operation amplifier is giving, and then it is not stable to use as an amplifier because there is no feedback. So open loop, definitely we use operation amplifier in the open loop mode for some applications. The best one is the comparator, which I discussed. So operation amplifier is used in closed loop. Then we can make amplifier, then we can make a filter, then we can make oscillator, and so on. So closed loop means with feedback. You might ask, what do you mean by closed loop? Closed loop means with feedback. Open loop means without feedback. So that's the difference. Then when you are using with feedback, then control over gain. So you can control the gain. So you will be getting a new gain that is called closed loop gain. Again, you can have control over bandwidth. You can vary the bandwidth, and then the circuit is stable because of the feedback. So then there are two ways you can operate. One is in open loop, another one is in closed loop. Without feedback or with feedback. Closed loop is called with feedback. Then again the question arises, you might have studied feedback. Then if you studied feedback, then the question is, there are two types of feedback. So when you have this operation amplifier, so that is your op amp, and then that is your internal gain. That the factory already set it. And then when you are operating in closed loop, then what you are having is, then you are having, this is a feedback. And then you are taking this output, so this is your input. And then, so this is your output. So output is Y. Your input is X. And then feedback fraction you are taking, and then you are connecting here. So when you connect here, there are two ways you can do. So then feedback is factor is K, feedback constant, which we studied in the ECD. So this will become K into Y. And then you are getting X coming here. So when this point, then you have option number 1. Either you can subtract input from KY. Option number 2, at this point, you can X plus KY. So then this one is called negative feedback. So then if your input signal is subtracted from KY, then that is called a negative, and then this is called a positive feedback. So negative feedback has lots of advantages, so that we will be using this one for amplifier, then this one for filter, etc. So lots of applications you will see negative feedback. But then where we use positive feedback? Do you know where we use positive feedback? Oscillators. So positive feedback means oscillators. Then the easy way to remember is, your signal is X, and then you are subtracting. So your input here is X minus KY is going to the amplifier input, and then that is for amplifier. For oscillator means you are building up some oscillations, so that you need to constantly add your signal. So that's the reason your input you are adding with the KY, again giving to the operation amplifier input. That one is amplified, again it is coming, and then it is going through the feedback loop, again subtracting. That's what is happening. So oscillator we will be using positive feedback, and then negative feedback is used for amplifier, filter, etc. In some filters that we will study, we will use negative feedback and positive feedback together, but then negative feedback will be predominating. That we will study later. Okay, so then now we know that so operation amplifier you can use in open loop or closed loop. If you are operating in closed loop, then you can operate again either in negative feedback or in positive feedback way. Now I am going to ask you a question. So I have got, so I am going to draw an operation amplifier. So this one I am connecting here. So this is a open loop or closed loop? Negative or positive feedback? Yeah, so because you know that your output you are taking subtracting, so here. But then if I draw like something like this, and then if I give this positive, and then if I give signal here, then it is kind of a positive feedback. And then we will come to the virtual short where we stopped. So when you have operation amplifier, we already discussed there is a virtual short. Virtual short means this operation amplifier will make sure that this input will be equal to this input. That is called virtual short. There is no short, but it will make sure that it is the case. So why we are getting, we already discussed it, because if this is X and then if this is Y, then this will be, it will make sure that at this point this is equal to, it should be X, but then this is equal to Y, so that X is equal to Y. You know what I mean? So here you are getting, if you are getting 1 millivolt signal, you will get 1 millivolt signal here, because operation amplifier will make sure that this voltage equal to this voltage. And how you can prove is your operation amplifier V out, that is here V out, which is equal to A0, that is the open loop gain of this operation amplifier, into V positive minus V negative. So we can write V positive minus V negative, which is equal to output divided by A0. Usually this A0 is a very big value. So if it tends to infinity, so you can write this equal to 0. So that is the reason V plus approximately equal to V negative. So that is the reason this will make sure that this voltage equal to this voltage. Then we discussed using this we can make amplifier, because how you can make amplifier without using. So when you have this positive, negative, and then what you can do is you get some. You put a resistor here, then you put another resistor here, then you give the feedback, and then you give here 1 millivolt, and then what will happen is if you put here 1K, 1K, then what will happen is operation amplifier will make sure that this is equal to 1 millivolt, because here it is 1 millivolt, here it is 1 millivolt. If you want 1 millivolt here, this is 1K, 1K, so this should be equal to 2 millivolt. So you can get gain 2. So by varying this one, using the idea of operation amplifier, you can amplify the signal. So this is amplifying because of the virtual short. Then we can derive the equation later. Then that is the reason people also discuss about virtual ground. Virtual ground means if you got an operation amplifier, and then I am going to ground the positive, then something like this. Then here I am going to give a signal. If that is the case, what will happen? Or I can connect, if you want an amplifier, maybe you might be familiar with like this. Maybe one resistor you connect here, and then this is R2, maybe this is R1. If that is the case, what is the voltage here? Yeah, this voltage equal to 0. So that's the reason this is called a virtual ground, because you got a negative feedback, and then this voltage operation amplifier will make sure that this voltage equal to this voltage. And then if it is a virtual ground means you can derive the equations very easily, which we will do later. And then this point is equal to 0. So whatever the current is going, it will come here. If it is an ideal operation amplifier, current going into the operation amplifier equal to 0. So that all your current will be going like this and coming back like this. So that is the reason the derivation is easy when you have feedback. Okay, now we will go back to the slides. So we discussed, yeah, we came up to virtual short. So now we know what is a virtual short. Then unity gain amplifier. So this circuit is a unity gain amplifier. As I said, your open loop gain equal to 1000 here, open loop gain. But now what we are going to find out is how can you say this is a unity gain? Using the feedback we can say when this is 1 volt, this will be 1 volt. So we get 1 volt here. But then if you want to use equations, you can say V out equal to A0 into V in minus V into. V in minus V into. But here V into equal to V out, because this V out is connecting to the V into. So you can substitute. Then you can rearrange V out by V in equal to A0 by 1 plus A0. A0 is so big because it's around 1000, because 1000 divided by 1000 plus 1, and then which is equal to 1, approximately equal to 1. So that's the reason you are getting a buffer. This is called a buffer circuit with the unity gain. Then op amp with the supply rails. So operation amplifier, sometimes you will be connecting here plus voltage, then you can also connect here to ground or here to minus voltages. So if you connect here 0, then here it is starting from 0 to a particular voltage. But if you connect negative here, you can get from negative to a positive value, which you already studied in the context of transistors when you have dual rails. It is called dual rails, dual power supplies. And the maximum amplification we can get is up to the power supply. So if you want to have more than 5 volt in your output, then you have to increase the rail power supply ranges. Maybe you have to make it 10 volt. Otherwise you will get a clipping. See, here it will undergo a clipping. See, it is flat. Then when you are using a operation amplifier, you can have 2 modes. 2 modes means in the operation amplifier, because you got inverting and non-inverting, then you can connect either signal. So this is your operation amplifier. Then this is a non-inverting terminal. This is inverting. So because of this one, you can operate as either as a non-inverting amplifier or inverting amplifier. Means you can connect your signal either to here or to here, or even to both. That is called differential mode. So if it is not differential mode, we are going to take only single-ended case. Single-ended case means you are applying signal to only one line. So you can operate either as a non-inverting amplifier or inverting amplifier. So from the name you can understand what happens to the signal. Non-inverting means you are connecting your signal to the non-inverting terminal, and then your phase will be same. Means if you are connecting signal here with feedback, then you are connecting a signal like this, you will get a signal here. Our assumption is we got the feedback. Then non-inverting means if you are connecting a signal here, it will be inverted here, because non-inverting. So now what we are going to do is inverting amplifier, and then the non-inverting amplifier. So non-inverting, first we are discussing the case of a non-inverting amplifier. So non-inverting amplifier, then our assumption is our A0 is very, very large, open loop gain. So open loop gain is very, very large, which is true. I have shown you some example in the last lecture. Open loop gain is usually very big. See, open loop gain, why I am taking that as infinity means in the last lecture I already shown you the open loop gain. See, here you can see the open loop gain is around 105 dB. So 105 dB is a very, very big value. So that's the reason that assumption is okay. It is valid. Then for this one, there are different ways you can derive the expression, but then the easy way is this way. So because you got negative feedback, your V into, what is the V into here? That is equal to V out into R2, because we are taking voltage across the R2 divided by R1 plus R2. And then we can also write V in 1 minus V into equal to V out by A0 from the equation V out equal to A0 into V in 1 minus V in 2. Then if A0 is a big value, I can write V in 1 equal to V in 2. Then, so I can write this is equal to V in 2, which is equal to R2 by R1 plus R2 into V out, which is equal to V in. So that is the reason here V in equal to V out, V in 1, which is equal to V in 2 because of the virtual short, which is equal to R2 by R1 plus R2 into V out. So we can write V out by V in, which is equal to 1 plus R1 by R2. So that is called closed loop gain. See, that is very important to see, because A0 is the open loop gain. When you have feedback, then you are getting a closed loop gain. So this gain you have the control. By varying the R1 and R2, you can control the closed loop gain, and then this closed loop gain is independent of your open loop gain. So this means you have the control by varying the R1 and R2. Like I am making an amplifier and I want to get gain 10. Yes, I can get gain 10 by varying R1 and R2. It's not depending upon the A0. So that is called a closed loop gain. A non-inverting amplifier returns a fraction of output signal through a resistor divider to the negative input. See, that's what is happening. With a high A0, V out by V in depends only on the ratio of resistors, which is precise, which is very precise. So that's what you are seeing here. So V out by V in, so that is called a closed loop gain. Please remember, closed loop gain, which is equal to 1 plus R1 by R2. Then inverting amplifier. So in the inverting amplifier, what is happening is in the non-inverting, see, you are connecting your signal to non-inverting terminal. In the inverting amplifier, you are connecting signal to inverting terminal, that is a negative, and then positive part you have grounded, then you got a negative feedback. In the inverting amplifier also, you will be giving negative feedback because an amplifier. When it is an inverting amplifier, again same, V out equal to A0 into V in 1 minus V in 2. So when A0 equal to infinity, V in 1 minus V in 2, which is equal to 0, so that your V in 1 equal to V in 2. So that is the reason this point is called virtual ground, because this is ground, so op amp will pull up this point to ground or pull down to ground. Maybe that is the correct way. Pull down this point to ground, and so this point is called virtual ground. So when it is virtual ground, we can write equation very easily. And if this is an ideal operation amplifier, or if you got infinite A0 or a or an open loop gain very large, then the current going from here into the operation amplifier is kind of negligible. For an ideal op amp, it is 0, but for a real op amp, it will be kind of nanoamps. So not much current is going in. So it is easy to write the equations. How can we write down the equation for gain here? 0 minus V out means 0. This is the voltage. This 0 minus V out divided by R1. So this is a current. Means current is coming from here. This is your signal. That signal is coming. That current, maybe I milliamps is coming. So I milliamps is crossing this R2, coming to this point. Then it is coming through this R1 and coming out. It is not going into the operation amplifier. So that the current coming to X, it should go out. So 0 minus V out by R1, which is equal to V in by R2, because at this point you can current law. At this point you can write this current is coming here and then that is going out. Then here you got V out and V in. When you rearrange, you get minus R1 by R2. See, now your closed loop gain is minus R1 by R2. Means you will be getting an inversion of the signal. So your phase of the signal will be changed. If you are having a positive cycle here, you will get negative cycle here. So that is the reason here you are getting a negative. And then again it is depending upon only the ratio of resistances, R1 by R2. It is independent of the open loop gain A0. So infinite A0 forces the negative input to be a virtual ground. Means because you got a very large A0 close to infinity, this point is kind of equivalent of this ground. But then in the non-inverting, you can see gain equal to closed loop gain, which is equal to 1 plus R1 by R2. So when you are using, you should be using the term closed loop gain, not just gain. Then people might get confused. Which gain? Open loop or closed loop? So closed loop gain equal to 1 plus R1 by R2, and then here it is minus R1 by R2. Then okay, so somebody designed this one. So now you have been hearing about non-inverting and inverting. So somebody designed a non-inverting amplifier, then somebody designed the inverting amplifier. Forget about the phase shift, because here you will be getting a phase shift. Means the signal will be inverted here. And the gain is almost the same in the sense R1 by R2. Here it is 1 plus R1 by R2, only 1 point difference. So that also I am going to neglect, because I am going to get a gain of maybe 50. And then here you will be getting 51, here you will be getting around 50. You know what I meant? Then my question is, for a voltage, as a voltage amplifier, which one is good? Non-inverting or inverting? So I'll give you maybe half minute to look at it. So non-inverting. Then I will give you half minute for the inverting. So you can tell me which one, because somebody can ask you, okay, we got two configurations. We don't care about the phase. We don't care about the plus one, one more gain. Then which one is good as a voltage amplifier? Means best. Inverting, non-inverting. So I got somebody said non-inverting. How about your answer? Somebody said inverting. Yeah, so non-inverting might be good. Why? Because when you look at here, your signal is going into the operation amplifier and input impedance of the operation amplifier is very high. But then when it comes to inverting, you got a resistance R2. So then that is not good. You don't have a very high impedance. Then there are basic circuits like a voltage follower, which we already discussed. Then inverting amplifier, we discussed. Non-inverting amplifier, we discussed. So there is one more category called difference amplifier. Difference amplifier means you will be connecting signal here and here, and then it's called a difference amplifier, which we will study later. And this, because we need some more time to study this one, because I will finish filters and then I will come back, because after filters I have to discuss about the project. Then we will be studying this difference amplifier. Then I also wanted to teach you instrumentation amplifier. So that's the reason this part we will hold on. So there is one more amplifier type called difference amplifier. Since we need more time, we will study this one later. Then type follower or voltage follower. Gain is approximately equal to 1, and then impedance, which is infinity if you are using an ideal operation amplifier. Then hence non-inverting, inverting, which we all studied. So meantime, please hold on with this one, difference amplifier, which we will study later. So next what I want to discuss is, people might ask you, what are the merits of negative feedback? So we will be using a negative feedback for the amplifiers. Then what are the merits? The first merit is called gain desensitization. Second merit is bandwidth enhancement. Third merit is modification of input and output impedances. Fourth merit is called linearization. So these are the four advantages, main advantages of negative feedback. Then maybe we will start from gain desensitization. What do you mean by gain desensitization? Which we already discussed. See, the circuit below is designed for a nominal gain of 4. So 4 means it is a closed loop gain, because its name is designed for a nominal gain of 4. See, this is a circuit. Determine the actual gain if A1 equal to 1000, A1 or A0, that is called open loop gain. Then the question is, determine the percentage change in the gain if A1 drops to 500. Means the question, in another way I can explain. So the gain desensitization. So if you got negative feedback, the advantage is there is called a gain desensitization. So you have got an amplifier. So you made an amplifier, and in the amplifier, first case is your open loop gain equal to 1000. Then you are getting some amplification, and then you are getting 4 into amplification with the feedback. So this is the feedback. You use negative feedback. So negative feedback. And then here you are connecting 10 millivolt, and then here you are getting 40 millivolt, because you got the feedback. But then open loop gain equal to 1000, A0 or A1, but then closed loop equal to 4. Then the question is, suddenly this one got burned, and then what you did is you replaced this operation amplifier, but this time when you went to shop, you got only A1 equal to 500. Then here you got 10 millivolt, then you need here 40 millivolt, that is a requirement. Then you will just replace it. Then this may be your feedback loop. Then you are not going to do anything to the feedback loop, only you replaced this part. So earlier it was 1000, now it is 500. Then the resistors are arranged for, we made it for 4. Then my question is, will I get 40 millivolt here when you use an operation amplifier with a lower open loop gain? You know my question. So how many of you think that we don't get 40 millivolt? So we will definitely get very close to 40 millivolt. That is called a gain desensitization. So that's what we are going to discuss. So that is a question. So this is the amplifier, and then K, your feedback fraction. What is feedback fraction? XF, whatever the feedback voltage divided by Y. So that is output, which is equal to R2 by R1 plus R2. And then K into A1. So that is called the feedback. So do you remember this one? Loop gain. R2 into A1 by R1 plus R2. So if K tends to infinity, X equal to XF, means which we already studied, because if this operation amplifier, your A1 is very large, then operation amplifier will make sure that this voltage is non-inverting equal to inverting. So you can say X equal to XF, which is equal to R2 into Y by R1 plus R2. and then closed loop gain, which we already discussed, which is equal to A1 by 1 plus K into A1. You know the standard equation, and which is equal to y by x. You can derive y by x equal to 1 plus R1 by R2, which we already derived in the previous slide. And then in order to get gain 4, you need R1 by R2 ratio equal to 3. So y by x, which is equal to 1 plus R1 by R2, which is equal to R1 by R2, which is equal to 3. So that is the reason you are getting. So if you get this ratio, you are getting closed loop gain of 4. Then what we are going to do is, first we are going to find out closed loop gain y by x when your A1 equal to 1000, means you are going to get the first case open loop gain of the amplifier equal to 1000, which is equal to your closed loop gain, which is equal to A1 open loop gain divided by 1 plus K into A1. And then you might wonder how this equation, from where this equation came. We already derived this equation for in the ECD in order to find out the closed loop gain. If you don't remember ECD, we derived this equation A0 by 1 plus A0 for the buffer. For the buffer, just now we derived unity gain. A0 closed loop gain equal to A0 by 1 plus A0, because their feedback fraction equal to 1. So A1 by 1 plus K into A0. So you can substitute A1 by 1 plus, what is the feedback fraction here? Feedback fraction equal to R2 by R1 plus R2, that is a K. Then you substitute here. Then our assumption is R1 equal to 3 times R2. Then you get gain 4. Like you can put 1K here, R2, then R1 should be 3K. Then only you get a gain of 4. Then you are going to substitute. So your R1 equal to 3 times R2. Substitute here instead of R1. Then you get 3.984. So that is the gain when you have a open loop gain of 1000. You get a 3.984. But when you replace this one with A1 of 500, just became half. Again, when you substitute, you get 3.968. See, A1 drops by half, but the closed loop gain changes only by 0.4%. See, so that your closed loop gain is independent of open loop gain. So that is called gain desensitization. So that is the reason operation amplifier you can treat as a black box. Once you design for gain of maybe 20 using the resistances, maybe you can replace that operation amplifier with something similar with the same pin configuration, but internal gain, you don't care about internal gain. You put it in, still you will get around, if you are 20, you may get 19.9, 19.98 that value. Because when you have feedback, this is advantage. Your gain is independent of open loop gain. Open loop gain is the gain set by the factory. So you don't have to rely on that one. So this is called a gain desensitization. Another one is another advantage we already discussed, that is called a bandwidth enhancement. So we can discuss in detail now. We already discussed the bandwidth enhancement. So what do you mean by bandwidth enhancement? So the bandwidth, concept of bandwidth is very important. So when you go to LM741, so when you go to LM741, you will see, maybe I should zoom. See, so this is open loop. So they don't give the closed loop, because closed loop gain they don't usually give it. Why? Because closed loop gain you can set it using the resistances. And they have given open loop gain versus frequency. So when you have this value, you can see 10 hertz, 100, then 1 megahertz, and then close to 1 megahertz, then your gain equal to 1, because 0 dB, which is equal to 1. Then bandwidth. So what do you mean by bandwidth? Bandwidth is the region where the gain is flat. Frequency range at which your gain is constant, that is called bandwidth. So if you operate your LM741 in open loop mode, so this is called open loop mode, what is the bandwidth? Around 3 or 4 hertz, that is a bandwidth. But then using 3 hertz, nobody can make an amplifier, because your maximum, because after that your gain is decreasing. So this is a range. So that is the reason open loop mode you can't make an amplifier. You need a feedback. Then when you do feedback, what will happen is you can increase the bandwidth. Then when you are increasing the bandwidth, you will be decreasing the gain. So that's what you do. So gain into bandwidth will be a constant. So I will come to that point. So bandwidth. So this is the closed loop gain, which is equal to A0 by 1 plus k into A0. So that is coming from this standard equation which we studied in the ECD, if you remember the slide. So now what you have to remember is closed loop gain, which is equal to A0 by 1 plus k into A0, which we already discussed. Now when you have feedback, your bandwidth will be enhanced by same multiplication factor, 1 plus k into A0 into omega 0. So previously for LM741, this omega 0 equal to 3 hertz. But then you can increase 1 plus k into A0 times 3 hertz if you are using a feedback, negative feedback. Oh, sorry, yep. So for LM741, the closed loop gain equal to A0 by 1 plus k into A0. So closed loop bandwidth, which is equal to 1 plus k A0 into omega 0, means this 1 plus k into A0, that much multiplication is possible when you have feedback, negative feedback. And then omega 0 is the bandwidth without feedback. So for LM741, omega 0 we have checked, it is around 3 hertz, very small. But then we can increase the bandwidth by feedback, negative feedback, then by 1 plus k into A0. But when you are increasing the bandwidth, your gain, open loop gain, see your closed loop gain, which is equal to A0 by 1 plus k into A0. So then you are reducing your gain actually by 1 plus k into A0. So we will come to that point. So that is the reason gain bandwidth, gain into bandwidth is a constant. So that's called gain bandwidth product. Okay, so from this slide what you have to understand is closed loop gain equal to A0 by 1 plus k into A0. So when you have negative feedback, actually you are reducing the gain. But then when you have negative feedback, you can increase the bandwidth by how much you decrease your gain. The gain and bandwidth are scaled by the same factor, that is 1 plus k into A0. K is the feedback fraction, A0 is the open loop gain. But in opposite directions, displaying a constant product. Opposite direction means when the gain is decreasing, bandwidth increases. You can do with feedback.
Is omega 0 means the gain is constant or 3 dB?
No, so 0 means 0 dB. You are talking about 0 dB.
So the omega 0 means like 0 dB?
No. Omega 0 is, when you come to the data sheet, omega 0 is the bandwidth without feedback. So here the omega 0 is somewhere here.
It is not 3 dB.
Yeah, 3 dB point here. Because this is in the dB. So then this is around 105. So 105 is coming here, 3 dB is coming somewhere here. This point, you know what I meant? So 105 minus 3 dB, so that is equal to around 102. So then 102 is coming somewhere here, see? That's around maybe 3 or 4 hertz. So that is without feedback. So you all know how to find out frequency response. So frequency response for the ECD, what you did is you took the amplifier and then you connected a sinusoidal signal and then you kept the voltage at the input constant. Then you varied the frequency. Then you found out the output. Then what you did is you plotted gain versus frequency. So have you done that one? And then when you did gain versus frequency, what you did is you kept the input voltage constant and then you varied the frequency. And then you found out output by input. Then you plotted like this. Then what you have got is gain started constant. After some time it started rolling off. When your frequency increasing, then your gain decreased. See, the gain decreased, and then that is called frequency response. And then Then you also did some kind of this type configuration where you got something like this, a mid-band response. And then this is you are getting, why? Because you are connecting these external capacitors. If you don't have these capacitors, usually when you characterize the amplifier, you will be seeing something like this in the open loop. So the operation amplifier, once they have fabricated the operation amplifier, then they do a gain frequency kind of a plot or a frequency response curve. The operation amplifier, they do it in the open loop mode, not in the closed loop mode. So you fabricated the operation amplifier, then they find out what is the frequency response for this amplifier, and then they do it in the open loop, and then they will be finding like this. The gain is constant, then after some time it start rolling off, and then they put it in the data sheet. So that is the reason in the LM741, when you see this one, see open loop, and then open loop, see, then their gain is constant, and then this is rolling off. So this is a high pass, band pass, or low pass. Which one is this one? Yep, low pass, because it's passing only low frequencies and attenuating the high frequency. And then for ideal operation amplifier, we will be saying, oh, the gain is constant under infinite frequency. But then this is for only ideal operation amplifier, which is not possible. When it is a real amplifier, what is happening is in the open loop. In the open loop mode, your gain is constant. Then after some time, see 3 dB. After 3 dB, then it started kind of rolling off. And then when it is rolling down, wherever the gain is constant from this 0 hertz to the 3 dB point, so that is minus 3 dB this point, that is called bandwidth. Means the frequency range at which your gain is constant, that is called bandwidth. And then it is rolling down. See, when your frequency is increasing, your gain will decrease, and then this gain means it is touching here, that is equal to 0 dB. So at this particular frequency at which your gain equal to 1, so that is called unity gain bandwidth. So that's the reason sometimes you might be hearing unity gain bandwidth. Then you know from the term you understood everything, because unity gain is unity, 0 dB, and then that is a bandwidth. That is a bandwidth. And then here you can ask, at this point you can get the bandwidth equal to maybe 10, and then your gain is very, very big, 10 to the power of 4. But then the unity gain bandwidth, that is equal to 10 to the power of 5. Unity gain bandwidth, but the real bandwidth is only 10, but unity gain bandwidth is 10 to the power of 5. Unity gain bandwidth means this is a range, this is a maximum range, means at this point you get a gain equal to 1. Then you might be wondering why we should worry about bandwidth. We definitely have to worry about the bandwidth, because when you take a music waveform, and then by the way, music signal, the audio signal, you are designing an audio amplifier. So when you are designing an audio amplifier, you know the range 20 hertz to 20 kilohertz. So that is the audio range. So somebody asked you to design an audio amplifier, then they have given you LM741. Then if you are using LM741 open loop mode, you can't make an amplifier. Even if you make something like for amplifying something, you have a problem. Your bandwidth is only 3 or 4 hertz, but then your audio range is 20 hertz to 20 kilohertz. Then what you will do is you might be clever, then you will record the music waveform from the microphone on the wave oscilloscope, and then when you display it, you will see, yeah, that is in the millisecond, see, and then here this is a music waveform. But then you might think that we don't need much bandwidth, because when you see this signal, if it is in the millisecond, see 4 and then this is 5, and then here it is only 1 millisecond. So you don't need, you might think, oh, this is you don't need much bandwidth. But this is a music waveform. When you take a Fourier transform of this, it might be looking something like this. So whenever you have some waveform, except sinusoidal. So sinusoidal, if you take Fourier transform, you get only one frequency. But if it is a square wave, if you take a Fourier transform of a square wave, you will see infinite number of almost sinusoidal wave. So you bring in so many sinusoidal waves, then only you can get a square wave. So when you take a Fourier transform of the music waveform, what will happen is you will be getting so many sinusoidal waveform of different frequencies, and then that is the problem. So when you are designing to amplify the signal, you should be thinking in terms of the Fourier transform. So this one got lots of frequency components. Then if your gain is constant up to only here, then what will happen is it will amplify some of the low frequency sinusoidal signals in the waveform constantly. All the high frequencies will be attenuated. Then what will happen? You get distortion. So that is the reason you need enough bandwidth. And then here is at the moment is bandwidth, and then this is unity gain bandwidth. But then when you look at the data sheet and then when you go through it, it's very interesting. So you have this open loop gain. Then when you come to this open loop gain, we are going to take this point. When you take this point, what is the gain? Gain equal to 80 dB, and then corresponding frequency is how much? 100 hertz. So 80 dB into 100 hertz, which is equal to 80 dB I converted into 100 hertz, that is equal to 1 megahertz. Again you come down through this line, you come to this point, which is equal to 60 dB. 60 dB into around 1K, again you are getting 1 megahertz. So along this line, if you multiply the gain and the corresponding frequency, what you are getting is a unity gain. You know what I meant? And then take this point. At this point, what is the gain? Around 105. And then your frequency is around 3 or 4 hertz. When you multiply, you get 1 megahertz. And then you come to this point. When you come to this point, 0 dB, that is equal to 1 into 1 megahertz. Again, you are getting 1 megahertz. See, along this line, when you multiply gain into frequency, you are getting always constant. So that is called a unity gain bandwidth. So you are along this line, when you multiply your gain and frequency, what you are getting is the unity gain bandwidth. Then from here, then you can make some amplifier ideas, because gain into bandwidth is equal to a constant. So if you multiply open loop gain and the bandwidth, that is equal to a constant, which is equal to unity gain bandwidth. Then if you increase the gain, you have to decrease the bandwidth. If you increase the bandwidth, you have to decrease the gain. So using this idea, you can increase the bandwidth. But then the question is, who set this gain? This gain is set by the manufacturer. How can you reduce the gain? You know what I meant? So you can increase the frequency. For example, if you can reduce the gain to 80 dB, what is the frequency you can get? The bandwidth. Yeah, you can get 100. If you can reduce the gain to 60 dB, then you can get a bandwidth maybe around 1 kilohertz. If you can reduce gain to 20, then you can get a bandwidth around 100K. But then the question is, how will you reduce the gain? So that is a reason we are using feedback. So then we use the feedback and then reduce the gain. So when you are reducing the gain using feedback, then we are increasing the bandwidth. You know what I mean? So that is the reason using feedback, we are reducing the gain and then increasing the bandwidth. So that is the reason here you have got the open loop gain, and then we reduce the gain using the feedback so that we are getting a higher bandwidth. So previously this is the open loop bandwidth. Then we connect the feedback and then we set the gain. We can change the gain, means it's in our control how much gain we want to reduce using the resistors. And then you reduce the gain and then you can increase the bandwidth. See, this is the closed loop bandwidth. So that is the reason when you reduce the gain by 1 plus k into A0, you can increase the bandwidth by 1 plus k into A0. So these expressions, closed loop gain, which is equal to A0 by 1 plus k into A0. So with feedback, you are reducing the gain from A0 to 1 plus k into A0. So this is the gain you reduced by 1 plus k into A0. But then your bandwidth, you increase it from omega 0, very small, to 1 plus k into A0 into omega 0. So when you multiply closed loop gain into closed loop bandwidth, when you multiply, you get A0 into omega 0, that is called unity gain bandwidth. So unity gain bandwidth equal to A0 into omega 0, and then unity gain bandwidth is the bandwidth or the maximum frequency at which your gain equal to 1. So when you multiply both, you are getting A0 into omega 0, open loop gain into open loop bandwidth. So that is the idea of bandwidth. See, using negative feedback, we can increase the bandwidth. So that now you can design an audio amplifier. You are using LM741, but then LM741 got only very small bandwidth. See, LM741 got only very small bandwidth, around 3 or 4 hertz. But then for audio application, maybe you need 20 or 25 kilohertz maximum, or even you can get 100. Then what you will do is you will design the operation amplifier. Then this is your operation amplifier, your positive, negative. This is a simple example. And then you are connecting your signal, audio signal here, and then you connect your resistors, and then that's all. Then using this resistor R1 and R2, and then you will reduce the gain to maybe 20 dB, and then you can get a bandwidth of 100K. See, so using feedback, we are reducing this gain and then increasing the bandwidth. So now your frequency response will be something like this. See, your frequency response. So that over this range, all the frequency components will be amplified in the same value, so that you don't get any distortion. So when you are designing an amplifier, you have to make sure that you are amplifying uniformly all the frequency components in the signal. Because if it is a sinusoidal waveform, because you got only sinusoidal, but when it is not sinusoidal, you have to make sure that you have to amplify all the frequency components. An example is when you have very high frequency signals. So we will study rise time, like your signal width is something like this. See, 10 nanosecond. So that is this width. So you are going to amplify something like this. Then what will happen is there is a rise time. Rise time means for this signal to rise from 10% to maybe around 90 or 80% is called rise time. So this one. So this is called a rise time. But then this width is 10 nanosecond. So if your amplifier got enough bandwidth, then what will happen is if your amplifier got enough bandwidth, then after amplification you will get same type of width, same type of rise time. So this is also 10 nanosecond. So this will be 10 nanosecond if your amplifier got enough bandwidth. If your amplifier doesn't have enough bandwidth, then what will happen is you will get it, but then you will getting spreading. So this 10 nanosecond will become maybe 200 nanosecond. You know what I mean? Because you are removing the frequency components. Oh, sorry. Because here what is happening is spread is happening because you are removing some frequency components, or you are attenuating some frequency components. So because if you want to make a narrow pulse, maybe 5 nanosecond bit pulse means you need lots of frequency components. Okay, so now that concept is clear. Next is the current source, which we already studied in the context of transistors. So that is the reason I have used the same slide. So current source means now we know operation amplifier, you can design amplifiers, but then you can also design another thing called current sources. Maybe somewhere it will be useful, but understanding the idea of current source will enhance the knowledge of operation amplifier. So that is the reason I have taken current sources as an example. And the current sources, when you have a voltage source and then when you have a resistance, then what will happen is you are going to plot voltage versus current. And then when you increase the voltage, what will happen? Your current will increase. And then depending upon this value of resistance, this slope will change. But still you are getting a constant, straight line, linear. Voltage increases, then the current will increase. But then if you are connecting a current source, the current source will make sure that the current is constant. So you vary the voltage or even you vary the RC, the current source will make the current constant. And then this current source you can design for a particular current, like 2 milliamps or 3 milliamps. So no matter what happens to the voltage or resistance, then the current will be constant. So that is called current source. Current source got lots of applications like driving laser diode, driving LEDs. and driving some sensitive equipment that is sensitive to the changes in the current. Then transistor we can use for making current source. Why? Because when you take a transistor characteristics, so you can see ID versus VDS, or for a MOS, or collector current versus VCE, then it will increase and then it will stay constant in this region. So if you are operating in the saturation region for MOS or active region for BJT, see the voltage is increasing and then the current is almost constant. It's kind of a current source. So transistor you can use for making current source, but then using transistor